Again. Morning, everyone.
Good morning.
Okay, great. I learned. Thanks. Alright, let's get started. So this is how it happens when you do a last minute presentation, true engineers. The video we were supposed to play against the video which got played. What we played was the financial one, but we have one for every vertical and you can go and visit that on the YouTube page of NVIDIA. But the one which is the main one has the latest demos of how generative AI is changing the world. And that was supposed to be played. But yes, a good beginning and a good warm up for us as well. With that, let me get started. So I think today's topic is more of hands-on, is what we are going to show. So I'm going to speak less. I'm going to hand it over to Meg to show you more stuff that you can deploy in the production environment and how you can take this learning back to your, your deployments when you go back home and try and get things done. But with that, let me get started with the introduction piece of it, right? So, well, I don't think so. The introduction to generative AI is needed today. But the first wave of generative AI is what we have already seen at scale. And that's where the model building and giving this model in the hand of every person on this planet was the achievement that I think probably ChatGPT has been able to achieve pretty well. Wave 2 is what we are seeing it today. And I think that's what we are all here to gather and learn how this wave 2 of putting these models in the enterprise data environment and taking it as a a consumption for our use cases is what we are witnessing it as we speak about it, right? And that's what we are going to cover about it. And these experiences are expanding on a daily basis. I mean it even within NVIDIA. When we say that we have X number of bots running in, the very next day when we wake up, that number has been changed, right? Because those many number of bots are going live, or those many number of use cases are getting into production as well. We have customers in the country today, which has crossed now 1,000 plus use cases in their production environment. Live, right here in the country, probably in Bangalore as well. We have a couple of customers who are talking those numbers. So, it varies. And these are just the basic ones which are the extreme most popular use cases that people talk today about it. But I can tell you that even power engineers in our company uses generative AI, and the use case is not 1, 2, or 3, they are in multiple of tens. Right? Power engineering teams of NVIDIA, which does a lot of work around power engineering in our chips and systems that we design. So I'm going into those depth what the second wave of generative AI we are talking about here. But how do we take these models into the production environment? That's the key aspect of it. And that's where NVIDIA has come up with something known as NIM. When this deployment of model needs to be done, where the evolution of these model building is taking at its own pace, deployment also is very crucial, right? And that's what is affecting, impacting each one of you in your daily life, essentially, right? Okay, I can see the hall is almost getting full. If you don't have a seat, we have the next room where the live broadcast is also taking place. Yeah, relay room. Okay, back to this. And that's where we have something known as NIM, right? NVIDIA Inferencing Microservices. Secured, gives you all sort of models that you can host on top of it. Think of it as a container which can be exposed as an API to your developers. It's as simple as that, right? Which means now integration of these models in your application in an API format is good, right? And it gets evolved almost on a daily basis. Varies from all these use cases that we can think of it. Biology to simulations to speech to language model to regional language model and so on and so forth. If you have your own custom-built foundation model as well, which you have started to work in your organization, think of it, you can integrate it in as well and expose it as an API to all your developers across all kinds of businesses that you have it. Doable, right? Where can you experience this? Simplifying that life, even if you don't have a GPU in-house, but you want to experiment these models which are there in the open source community, in your applications, we have something known as build.nvidia.com. You can experience all those models as an API exposure over there. You can first try it. If you want to integrate that with the API exposure in your environment, you can do that as well. And once you are confirmed that this is the model and this is the API that you want to get exposed, you could download that container and get started to integrate in your environment, having where you have a GPU with whatever type of GPU that you have it. Okay? Well, having said that you can do these deployments in play, and NVIDIA is trying to simplify the deployment aspect of the story. As we interact with most of our customers, and I'm really proud to say this, NVIDIA is the only company which is an AI company working with every other AI company on the planet. The learning curve is, data is the most important thing in the whole cycle that we're talking about, because it's very customized to the requirements that you have, right? Even if it's as simple as PDF-based RAG pipeline implementation, your data would be different versus my data would be different, right? You might have tables, I might have engineering architect, drawings, and so on and so forth, right? And thereby, understanding this data flywheel is very, very crucial, right? And that's where a lot of learning curves that we talk about it, and that's where I will, hand over to Meg, that needs to come into play. And we will teach you both the methods that NVIDIA is trying to bring it in, which is the open source way, where you today have so much of development taking place. The second one is NVIDIA is trying to build now a lot of these examples for your ready reference use cases, with model trained specifically in the datasets of that example, and thereby you can take the fastest route of deployments in your environment, is the phase that we are talking about. With that, I want to invite Meg to show you how the theory looks like, and then show you how the practical deployments also takes place. So what do you make?
Thank you so much, Julian. Hello, everyone. So if you actually see today, and I'm sure, right, for every developer, the most important thing is that, hey, where can I actually go and start trying out these things? So what we have really done is that we have made a GitHub page with the name of Generative AI examples, where we have sort of bucketized into these 3-4 categories. The first category is where people are building their own RAG workflows, which are highly used by the community. So we have a community section for that. Along with that, we also have API endpoint integration with most of these widely used RAG frameworks, like Index as well as LangChain. And as Jigar was mentioning, we also have our own RAG blueprints. These RAG blueprints are essentially very specialized workflows for building RAG pipeline on different industry verticals. So I'll give you an example. So if you see these, we have recently published 3 of these, and our intent and goal is that every month we'll be coming up with new versions of these blueprints for different industries and different workflows. The one that are currently available is these 3. The first one is digital human for customer service. Essentially, what you see here, and I'll show you the exact blueprint of what are the different microservices that goes in terms of building this kind of a digital avatar that can essentially act as a customer service bot for your end use case. What are the different microservices, what are the different models, how are they all connected together? We'll talk about those details in a couple of minutes. The second one is the multimodal PDF extraction for enterprise RAG. Now, I'm sure for all of you who have been working on PDFs, especially when you need to handle things like tables, flowcharts, table within a table, image within a table, or probably different kind of images. I'm sure you must have faced a lot of issues. A lot of these solutions that you see out sometimes don't really work that well. And I'm sure everybody who uses OCR must have seen that you're not really effectively able to capture the structure of these flowcharts or tables. So what I'm going to share with you today is some of our learnings of how we have gone about addressing and extracting information from these kind of structures and unstructured data within PDFs, and what has been some of our learning experiences, and that's how we have built this one more back. We'll talk about this in obviously more detail. And the third one is for basically virtual screening for data sets. Essentially, in the agent blueprint, what you really get is the bottom part. These are live application examples which have sample data associated with it. It has a reference code base. It has the microservice architecture, as well as all the necessary tools for you to run your own data flywheel. Like Jigar was mentioning, building this data flywheel for your generative AI application is the most critical thing. Why? It's because when you build the first iteration of the pipeline, you will notice that you are still making a lot of mistakes. Because these models and the entire thing is very probabilistic in nature, you're never gonna achieve that 99.9% accuracy on day zero. Okay, so you need to essentially work on the entire life cycle. That means get your enterprise data in, use the right methods in terms of ingesting the data, building the right pipeline, and then deploying it out and making subject matter experts or the user of the system use it and give you feedback. And this feedback that you get from them is essentially going to help you to go back and improve the way the data has been ingested. And you need to keep doing that again and again over months and months till you reach to a point where you feel that, okay, you know what, now it has reached to a point where I really feel that it is started to generate more and more business value and it's more accurate than what it was 6 months back. And this is extremely critical. So what you've realized is that just using the models even out of the box is not going to solve your problem. You need a flywheel where you can fine-tune parts of these models. Can be the LLM model itself, can be the model that is embedding these text chunks, or it can also be the re-ranking model or even the speech models. So what we have provided is the right tools for you to customize as well as orchestrate and deploy these pipelines so that you can start with this entire data phase. Now, typically, people ask me that, okay, Nick, this sounds good, but how do I go about really running these things? And for that, it's always important to look at the real workflow and the steps of doing that. So if you see, what we've really done is, if you look at things, it's essentially a container that has the model, but there are a couple of interesting things inside of it. And I think the most important thing that would matter to everybody is the fact that how do I improve my performance? Most of the time, we keep hearing from people that, hey, we are deploying this model, it's becoming expensive. But when we actually start talking to them, we start to realize that people are not really applying any kind of low-level optimization on the model to improve the throughput. A lot of time people just take the model as it is and just use it out of the box. But that's not really the right way of deploying these models. What is extremely critical is to understand how you take the model weights and apply low-level compilers to compile this model and make it more efficient in terms of inference. And there are these different axes of optimization that you can run through. I will talk about those optimizations in a bit, but let's look at it. So here what you see is that there is a very simple document command that will pull the container image from our NVIDIA NGC repository, which is again an open source repository available from NVIDIA. Once you pull the container on your underlying hardware, the first thing that you need to really understand, at least the container needs to understand, is what is the underlying GPU that's being used. Because you see, based on the underlying GPU, there are a lot of parameters that you have to start deciding on. Okay, I'll talk about those parameters in detail in a bit. So the underlying hardware parameters are extremely important to decide what kind of optimization should you be doing. So to give you an example, you might have certain hardware that allows you to do FP8 optimization. So typically, if you see, most of the time these models are trained in a combination of FP32, which is floating point 32, and FP16 or brainflow 16. But when you deploy these models, you want to apply some kind of quantization. That means you have to bring down the precision so that the size of the model decreases as well as the compute efficiency improves. That's where what we have really done is that we have built hardware platforms with each generation and we have added support for lower and lower precision. In our previous architecture, which was the Hopper series, we had this new precision called as FP8, which is floating point 8. And what we really see is that in all the Hopper generation, if you are not using the FP8 cores, which are specifically built for running inference as well as training, then you are basically not taking the full advantage of the hardware. So understanding what is the underlying GPU type is extremely important. What kind of low-level precision does it support is extremely important. What we have done in the latest generation, which is the Blackwell generation, is that we have gone a way further, and from FP8 we have gone all the way to FP4 as well. So again, understanding the hardware and what kind of precision does it support is extremely important that I think people should really think more about. Second is that you have to cache the model so that you can use this compiler. The name of the compiler is called as TensorRT LLM. And the goal of TensorRT LLM is to basically do these 4 kinds of optimization which I'll talk about. First, obviously, as I said, is quantization. That means how do I bring the precision down from the precision on which it was trained, which is BF16 and FP32, how do I bring it to, say, FP8 or even FP4? So you need a compiler that allows you to do this kind of quantization. The second most important thing is that if you look at these models, okay, what are they really doing? At the end of the day, there are these different kind of mathematical operations that you're applying layer by layer. And typically, these operations can be filled into these different kind of buckets. The first bucket is called as matrix multiplies that you use to add. The second one is called as quantized operations. These are typically your activation functions like say sigmoid, relu, swigu, and so on and so forth. And the third kind of operations that you have are more of reduction operations, something like batch normalization, layer normalization, and so on. Now, what really happens when you are executing this model is that you are calling each of these mathematical operations one after the other. But you are not really fusing them. What does that mean? That means if I have, say, a matrix multiply followed by some quantized operation followed by some reduction operation, rather than calling them individually, can I fuse these operations together? So rather than doing, say, 5 function calls for 5 operations, can I do one function call and do all the 5 operations together? So how do you really fuse these operations together and make sure that the function call are less as well as the movement of these tensors in the memory is as less as possible? That's second layer of optimization. These are the two most critical ones that you should think about when you're basically trying to optimize these models. So the TensorRT-LLM compiler will take the model which has been downloaded from the cache and it's going to apply these TensorRT-LLM level optimization. Now, what we've really also done is that outside of TensorRT-LLM, there's another backend that people generally prefer, which is called as VLLM. So we support both of these two backends. You can choose to run it with all the optimization from TensorRT-LLM, or you can choose to run it natively in VLLM as well. Okay. So let's go to the next part, and this is again a very important part to think about. So if you see in terms of performance, what are the two key metrics that people generally care about? First is latency and second is throughput. These are the two main things. And you see that whenever you're trying to decide, hey, what should I optimize for? It's very important to take the design decision that, hey, which parameter is more critical for me? Because you see that you cannot always optimize the latency as well as throughput. There is always this tug of war where you need to take some kind of a trade-off. So I'll give you an example. So what does latency mean in this scenario? So think about it like this, right? Whenever you're trying to talk to any LLM model these days, you type a question and then it starts generating token over a period of time. So you see what it's doing is that it's generating this token across every millisecond and then it is returning those generated tokens on the UI interface where you see this. Now, if your latency is high, the time for the next token to be spawned on that UI becomes much more higher. But in that case, what you are able to achieve is that you can now handle a lot more concurrent requests on the same underlying infrastructure. That's trade-off number one. Or if you feel that, hey, maybe the latency is the most critical thing, and it's okay even if I'm able to serve less number of people. In that case, the most important thing becomes that, hey, how do I deploy this in a latency sensitive manner? Because I have a very strict very strict SLA that my tokens have to be generated within this particular time frame. And again, these are just not related to LLMs. You can actually apply this for also computer vision as well as for speech tasks like speech recognition and speech synthesis as well. The same logic also applies there. So if you see here, based on the GPU architecture, what you really need to decide is that, hey, because these models are going to consume some kind of memory, it is also important to understand that, hey, which GPU should I choose for? Does it mean that, hey, if my model is taking 16 GB, is choosing a GPU with only 24 GB going to give you the best TCO? Probably the answer to that question is no. So do not always correlate the size of the model with GPU memory. That's not really the right way to think about it. Why? It's because you see that whenever you're trying to run these models, you have something called as a KV cache. And that KV cache gets generated and the memory allocation happens during runtime. So in this particular case, what I'm trying to show you is that you have these different GPU architectures, and you might have a scenario where you might have small models, which might just take a single GPU, or you might have multiple. You will have large models for which you need multiple GPUs. So you have an option to select that, hey, should I choose one GPU, two GPU, 4, or probably 8. And then you decide whether you want to optimize for throughput or do you want to optimize for latency. And based on that, you also get to choose what precision you want to deploy this model. So all these are basically like different kind of permutations and combinations. And what we have done is we have created all these permutation combinations as different optimized profiles. And we can basically choose these optimized profiles based on your requirement that you have. And again, the same logic also applies for other all kind of models. So previously, what I showed you is for the AP model, and the next one that I'm basically showing you is for the CP model. Okay. Now let's come to the real benefit of it. Right? What happens after you do all these fancy things? So if you actually see here, this is for the Llama 3.1 7AP model. You can see that the throughput actually doubles up when you do apply these kind of optimizations in place. So what you see is that on NIM on, you're basically using the DRT LLM compiler with FP8 precision with an time to first token of 1.7 seconds and the inter-token latency of almost 40 milliseconds. In the second case, you are basically doing the NIM off version of it where you are not using the FP8 precision. Then you basically get about 1900 tokens. So you see, by using FP8, your throughput essentially doubled directly. Similarly, when you do it even for smaller models, you see that the gains are also pretty well there. So again, the point I'm trying to make is that it's very important wherever you're deploying these things because cost is a very important criteria for organization. Please make sure that you're using all the right kind of optimization to deploy these models because that is how you're going to lower down the cost. Again, this is another example of the Mixtral MOE model. Before this, we had the Llama 3.1 series, which are more of dense models, like Eco style models. And then here you have Mixtral, which is basically a mixture of expert model. Okay. The next important thing to talk about is the retrieval model itself. Now, again, if you look at a RAG pipeline, you don't only have an LLM model. You have these different kind of models which are stacked together to build your overall RAG pipeline. So one of the most important parts in this pipeline is the retrieval service. The retrieval service is essentially responsible for doing three things. The first thing that it is responsible for doing is that when you have your raw text or image or whatever that format will be, you need to encode that information in some kind of an embedding. An embedding is nothing but just a dense vector which has some kind of semantic meaning of that text or image stored in this vectorized format. So the embedding model will essentially take these text or images or whatever that input format is, depending upon the modality of the embedding model, and it will embed this input text or image into an embedding space. And then you take these embeddings and then save it into something called as a vector database. And these vector databases are essentially used for storing these embeddings, and whenever you send a query, the query again gets embedded and then gets sent to the vector database. And then you do something like a dot product and you find all the most relevant embeddings associated to that query. And then you retrieve them just like a typical search, and then you use that as prior context for your model. So now let's look at a basic RAG workflow. Okay, this is how the most generic ones would look like. You have some knowledge documents, and then you will load the document. You do some kind of tracking, and then you will use an embedding model to embed that and store that in your vector database. And then you use that vector database as a search mechanism, where you put the query, and then you get the most relevant context. And then you take these contexts to an LLM to start generating the answer by saying that, hey, given the above context, please tell me what is the answer for and then the query that you have. And it will start generating the answer. Now you see that people are now moving towards more advanced versions of these RAG workflows. And in that particular case, you see that there are a lot of these new and interesting things that are coming up. On the knowledge document side, there are two kinds of things that are important. The first is how do you parse multiple documents? And trust me, like I said earlier, everybody who has worked on PDFs, who will have tables, charts, images, and other modalities, it becomes very critical to choose that, hey, how am I going to parse these different modalities in my PDF document? So you need to have a multimodal document parser. I'll talk about some of our best practices that we have learned over a period of time and share in the upcoming slides. So you have a multimodal document parser. We'll deep dive into this specific area as well. And then on the second side is that you can use this knowledge document itself to do, curate the data either for your retrieval model or for even fine tuning your LLM model in order to improve the accuracy of the overall pipeline. Most of the time, what happens is that we just build a RAG and just start using it as is. But we do not think about that. Hey, how are we going to create the right data set for fine tuning my embedding model as well as my LLM model itself. But this is very critical when you are trying to build something which is production grade. You need to use your knowledge documents and then convert that to LLM trainable data. In this particular case, the kind of format in which you'll be structuring that is like QA based. So to give you an example, if you have a document that talks about, say, let's just take a simple engineering org who have these documents where you have documentation. Now, every section will have some headline and about a specific part or function, and then it will give you more description that hey, these are the different functionalities as well as the different parameters that it takes. Now, imagine that now you can use LLMs on top of this data itself, and then you can create QA pairs. Now, by creating these QA pairs, what you are really doing is that you are creating a data set for training your LLM model. And this has become very important these days. Outside of that, you can also use these headings and the data associated with that heading to generate your data for even fine-tuning your embedding model. Again, pretty simple. The only thing is that you need to start doing it, fine-tune it, and then look at the overall analytics. On the third part is that query itself, like how to improve the query that is coming in from the user. Now, why do I say that? I say that because you see that a query can paraphrase in multiple different ways. And the way it is paraphrased also becomes important because if you look at your vector database, you are just doing a similarity search. And sometimes similarity search, just the way it was paraphrased, you might get different retrievals itself. And hence it is important to sort of do two things. One is that generate different paraphrased queries for your specific answer, so that even a paraphrase, so that we can basically create this mapping of the same answer to these different paraphrased versions of the query. And second is how do you maintain chat history for long conversation. Now again, this is very important because typically you want the system to have some kind of relation with the conversation that we are having now, and probably the 5 previous questions that we had asked previously, and you might want to just give some generic reference to say probably query 1 and then try to get an answer. So how do you rebuild efficient chat histories? How much should you maintain that window? All that becomes very important while doing this. And another important thing is re-rank. A lot of times I've seen people do not use the re-ranking model, which is after your embedding retrieval, you need to use something called as re-ranking. What does this mean? That means that, say for example, you have asked a query, the query got embedded, it went inside your vector database, and it gave you, say, top 10 chunks of document. Now, when you're getting these top 10 chunks of document, you do not want to take all the 10 chunks and then feed it to the LLM. Because if you start feeding so many chunks, you see that the context window of your model starts decreasing. And in order to address that particular problem, you should be seeing that, hey, how do I filter from these 10 retrieved chunks to small number of more relevant chunks? And that is where you bring the model called as a re-ranker that is essentially responsible for sorting out that out of these 10 retrieved chunks, how do I only pick the most relevant top 2 or top 3? So that your context window doesn't get bloated with so many chunks. And so again, re-ranking again is extremely important, and we have seen that it absolutely helps to improve the accuracy. Now let's go to the next part. That means in terms of the multimodal document parsing, what are some of the things that we should be thinking about? Right? Because you see, at the end of the day, you might have these different modalities within your PDF documents. So the most simplest one is in case of PDF documents, you might have title, you might have text, you might have image, as well as you might have table. Now, if you just run a simple OCR, it's not going to be good at extracting these kind of things things like say table or images, because it doesn't understand the semantics of that particular modality. It only knows that hey, here is a text and just go ahead and extract that text. But how is that text structured in that particular modality is extremely important. And that is where what we have seen is that using these vision language models have become extremely important. So I'm not sure how many of you are continuously up to date with the newer models that are coming up, but there have been some really good releases like say the Quen 2VL model, then you have the Pixel model, and then recently even the Llama model came with a new variant which is Llama 3.2, which has vision capabilities as well. So you can take any of these open source vision LM models and use and prompt it in a way that you are able to effectively describe these tables and images. And then use that text document, use that text description to basically do some kind of retrieval and query on top of it. And again, we have found this method to be extremely efficient and really helpful for solving a lot of our problems where we have these different modalities. But once you run it through this VLM, which is a visual language model, can you just use it as it is? Most of them what we have seen is that typically what happens is that we sort of try to convert that into a JSON format, or we ask this model to extract it in a specific JSON structure. But there are certain times where you might see that there are some errors or challenges, and maybe they have missed one quotation mark or one curly bracket. In those cases, it's also important that you use again a text model to make sure that you're correcting some of these mistakes that could possibly have come from the vision model, so that you can ingest it directly for your end application. So we again use an LLM on top of the outputs coming from the visual language model to make sure that the structure and everything is proper, and if there are any of these typos or syntax mistakes, the LLM will basically go ahead and fix those. So this is one. The second one, what we have also seen is that in case of HTMLs, mostly rule-based systems do work very well, because you exactly know what kind of markers do you want to put and how do you want to extract that. So rule-based systems for HTML works pretty well. Again, for images and even in PPTs which have images, we have seen visual language models be very helpful. There are also some cases where people do not want to describe the table as it is and want to maybe say just extract the exact table and use that for doing real-time text to SQL query as well. So even that is possible. In one of our pipelines that I'll explain further, you will see that we have two kind of models. The first kind of model which specifically detects these tables, and second is a model that can keep the structure of the table as it is and extract that information out so that you can store it in some of your databases as well. So all those things are also possible. I'll talk about that also. So I'll give you an example. Sorry, sadly I'm sure the right part of the text is not that visible. But let me give you an example. So here we had this particular diagram, and when we used an OCR, we saw that it wasn't working that well. That means it was not able to effectively extract this entire structure properly. And hence, when we used a vision language model to extract this, you see that it was effectively able to put a heading of qualification and then put all these headers beneath it as subparts. This was again, these kind of things actually help, and these are the kind of things that you really want to see in the real world scenarios. Okay, let's move to the next part, which is the digital human part. That means I talked about that digital human blueprint, but what really encapsulates this blueprint? And it is important to understand that wherever you're running these kind of workflows, you will have these multiple models working together, and you want to make sure that it gives you a seamless and a real-time experience. If the bot starts replying after 10-15 seconds, I'm sure nobody's going to use such a system. So you see that what you have done in this case is that you have a user persona, which is on the left side, and then you have a web front end. The web front end is responsible for taking in the audio and showing a display where you have this digital human that can talk back to you. And all of that goes to an audio video streaming API gateway service. And then you have something called as an ACE agent. So the ACE agent, you can think about the ACE agent as something that talks to the RAG, which is basically your text part, which is text in, text out. but it also talks to the audio part of the pipeline. So if you look at a conversational bot, in that case, you need to have a speech to text system that will translate whatever you are saying into the text format, and then you use that text as a query, send it to your RAG application, and then you get some kind of a streaming answer back. That means the RAG system will start generating token by token. Once you start getting this token by token, do you wait for the whole generation to get over and then apply text to speech? If you do that, you see that your latency is going to be extremely high. You do not want to do that. And that's where what you really end up doing is that you take those streaming tokens that is coming in from the RAG system and then pass it to a TTS model that can take these streams of tokens and then also generate the audio part from the text in chunks. Because typically in a TTS system, this is how you must have experienced it. You put a sentence, it will go, and you will get a whole audio that has the entire generation. But you see, even in this particular case, you need to wait for the whole text to get generated. But in case of streaming setup where latency is extremely critical, you are sending it chunk by chunk. And you want to generate this audio chunk by chunk while making sure that no two tokens or three tokens that are being passed, there is enough overlap so that it doesn't feel like it has missed any words. And hence the streaming TTS becomes extremely important. Now the TTS system, which is text to speech, will generate the streaming audio in real time, and then will send it to and it will send it back to the ACE agent, who will then route that audio back to something called as an audio to face. So what is audio to face? Audio to face is basically one of our microservices where you have say a humanoid created in this virtual platforms, like say for example Unreal Engine or others. And then how you take the speech that is coming in from the TTS system, which has the answer, and make that humanoid basically say that same thing while making sure that the synchronization of the lips with the words which are being spoken is of exact match. Because you see that if the lip movement is different from what is being spoken of, you're going to feel a little odd. And hence we have something called as audio to face that makes sure that you are superimposing the speech with the lips and the synchronization is in place. So that the audio to face is basically responsible for generating that animation, and then it goes to the animation graph, which then goes to another neural render engine called as the Omniverse render, and then that rendered output then gets sent to the audio video streaming gateway, and then that gets sent back to the user on the UI. Again, extremely, there are multiple moving components, but we have made this workflow available so that even if you want to go and deploy this in your environment, you can go ahead and do that. Okay, let me talk about the multimodal blueprint also in detail, but in this case, instead of the vision language model, I'm going to specifically talk about how you do things like say chart extraction. So in this, you see what we have done is that you take this document and then you apply this object detection. Again, I'm going to talk very specific to charts in this particular case, right? So you basically apply an object detection model that will sort of detect that boundary of where these charts are, because you might have an image or a PDF page where you might have text somewhere and you might have some section where you might have the image and the chart. And post which what you can really do is that you can then apply something called as the chart element detector. And post which you can do something like the deep plot model, which again is a visual language model that will sort of extract the table, and probably for the rest of the text part in the document, you can use something like an OCR. Because in the text part, OCRs work pretty well. But only when there is some kind of a structure that is where you want to face some challenges. So that's on the multimodal extraction part, and then you send all of that to your post processor, which will basically combine the text, the charts, and the tables, all of them together, combine that into one unified format, like a markdown format, which is easily ingestible and can be chunked properly inside your vector database. And then I'm sure the rest of the components seem to be quite familiar to all of you. Now, till here I was talking about digital human blueprint as well as the multimodal PDF blueprint. But let me also talk about where are we seeing that these vision language models are being applied for doing video analytics in a much more efficient way. traditionally we used to build these video analytics pipeline where we had these object detectors, object classifiers, trackers, and we used to use that metadata generated from these 3-4 modalities, and then we used to create these insights directly. But now, with the help of vision models and which can again be applied to images as well as to videos, we are now able to actually extract more rich and contextualized information rather than the labels which are part of your detector and your classifier and your tracker. What do I mean by that? So let's take a couple of examples. So you see that what we are seeing is that a lot of people are trying to apply these vision language models for building visual AI agents. One example that we see on the top is that you have a video where probably there is some kind of an incident that is happening. So in this case, let's assume that you are trying to build maybe a security threat detection use case where you want to deploy it in ATMs. Where say for example, if there is a thief who wears a mask and comes and puts his face on, puts his hand or something on top of the camera and is trying to obstruct the view where he's trying to do some kind of malicious activity. Now, if you were to do it from the traditional method, you might think of that, hey, how do I detect this person first? Then, how do I detect whether this person is covering his face or not? And third, then we'll also try to do that, hey, is this image getting somehow blacked out or not? So you have a lot of these, very defined rules that you're trying to apply through these object detectors and other models. But now, instead of that, if you just apply a visual language model, it will become a lot more easier because then the visual language model can tell you that, hey, a person has entered this premise. He's wearing something on his face that is hiding his identity, and it seems like he's trying to look at the source from where this is getting viewed, and I can see that he's trying to put something to obstruct the view. The visual language model can describe all these information directly on top of these images. So you can essentially create these kind of incident reports and survey which are a lot more meaningful. So let me show you some live examples, right? Because that is how you're going to relate a lot more. Let me play this video. The audio. Yeah, so as you can see, there are certain examples there which basically show you that how these vision language models are becoming helpful. One of the examples that I found very interesting was the one where the person was trying to tailgate. Right now, if you want to do it through object detection and classifiers, trust me, that entire thing would have been a nightmare to solve because then you have to put these different kind of rules and then make the detectors to detect those kind of specific entities and so on and so forth. Again, extremely complicated rather just use a visual language model to just describe the entire system. And let me talk about some of these models because at the end of the day, when you go back, I want you to go back and try out these things. So you see what we have done is that we have created the limbs out of a lot of these visual language models. And what we realized is that it's important for you to deploy this on your own and try with your own data set. So you see that there are these two kind of specialized models that we are building in terms of names. One are visual language models like 5-3 Vision, Neva, Florence 27B. Now we have the Point series, Cosmos, and Valley and so on and so forth. And then we have computer vision specific names like you have for OCR, OCD, retail object store detection, visual chain management, and so on and so forth. So on the right side are very specialized traditional computer vision models, and on the left side are visual language models. All these are available. You can basically go to our build.nvidia.com page and you can find all these models in this section. Okay. Plus, we are also open sourcing a lot of these new sample apps that we can go ahead and try. Right? So you can see that this is one of the example canonical workflows where you have these different paths. Now, again, when you're trying to do video analytics, you see that there are these lot of different parts where you do things like frame decoding, subsampling, and then you are trying to create these requests. And then you're sending these requests, that means chunks of these images which you have chunked from the video itself, and then you're sending it to the visual language model. If this VLM model only supports images, okay, there are these two kind of models. You will find certain models that only support images, in which case you have to chunk the video into these specialized images and then keep sending it. And then there are the second set of models which are trained on images as well as videos. But obviously there will be some kind of a cap of how many seconds it can support. In those kind of models, you can directly feed the direct video itself. So again, depending upon what kind of model you choose and what kind of sub-modalities it support, you'll have to see how you pass your input to that. Let me show you another example of this table. Again, you can go and find all these examples in Metropolis new workflows. So basically, what this is saying that describe the scene in one sentence. Right? You can see that it's basically creating the responses here. You see, doing all of this through traditional detection is would have been interesting, right? Because then you have to add a lot of custom rule-based things, different detectors to do all of that. Yeah, so all these reference apps are available on Metropolis new workflows GitHub page. Let me show you some of more of these examples, right? So another important thing that we are seeing is that people are becoming more and more interested also in semantic search. That means, given a text description, can you go and find all those images where a similar incident was happening? This is extremely important, especially in say, some of these say police departments. Now, somebody wants to say for example, say that, hey, I want to find out all those images and videos as well as the timestamps where, there was somebody who was trying to do some kind of a violence. Let's say whatever example, like, hey, somebody is trying to hit somebody, okay? And then you just put in this much text and it will go and retrieve all those images where such an incident was happening. It will cluster all of that together, give you the exact timestamp of from the source of the video. And then now imagine the person who is on the other side feels so much relaxed. Otherwise, if you look at the more traditional way, you have to look at that video, look at the object detector, somebody will basically say that, hey, it happened at this particular frame. Trust me, extremely time consuming. And hence, semantic search has become very important. And trust me, this can be used for a lot of other use cases as well. So here what you see is that we simply have this model called as NP clip. And this model is basically going to embed all these images and it's going to embed it based on the meaning of what's happening in that image. And all of that again is stored in a vector database, and whenever you type this text query, it will go and retrieve all of this from the vector database. And it will also give you these plots of, like a testing plot of, if you're, say for example, if you type a description like, hey, find all the images that have some kind of a, fight happening, it will go and pick it from a specific part of the vector database, and it will also show you in that entire plot as to what are the neighboring images also associated with. So that even if you want to say explore through that semantic space, you can go and query that as well. Another one is structured text extraction. So here what we have is, say for example, you take upload an image, something like say a PAN card document, digital identity document, and now you want to basically structure all the information given inside of this in a proper tabular structure because you want it to save it in your database. We can basically use one of the workflows that's again given here, where you put the field name, the field description, and then choose the corresponding model, upload the image, and then click on process. And it will automatically do all these things for you and save these tables directly as well. Okay, Now, what I'm going to do is that I'm going to show you probably almost the last demo of my slide, which will show you another example of video summarization. So here your chunk size is 20 seconds. That means you're going to basically process 20 frames together. Yeah, so you can see that it has basically given the timestamps and what was happening in some of those timestamps. And again, this is more to do with unsafe behavior and operational inefficiencies. It's very specific. You can obviously customize this for your end use case and whatever you want to probably sort of extract information from these kind of videos and stuff. Yeah. So a lot of these things, everything we have made it open source. Our goal is that hey, how do we empower the developers and help them to build these workflows much faster rather than trying to do it from scratch. So yeah, probably in the last 8 minutes, I'll see if there are any questions. Okay, 8 minutes. Okay. So yeah, maybe I'll spend a couple of minutes for questions.
Hello. Yeah, thanks. Thanks. Very nice presentation. So one thing that we have learned so far, implementing their applications, is that making your retriever is the most smart thing that you could do, rather than working on the model side. Now, making the retriever smarter again need few things. You have to have a better extraction layer. You need to have a better chunking strategy and all that stuff. Now, we've been seeing that PDF, Word, presentations are still okay to do the extraction layer. What is your key experience around extracting from something like Excel, worksheets, and again, because that's one of the place Excel where people misuse Excel actually. So they try to put in everything. So what's your experience around how to do extraction of the Excel data?
No, again, that's a very good question. That is where I go back to in the multi-modal PDF section. You must have seen that there was a specialized. So again, there are two ways which I explained, right? One is that you use a vision language model to describe the tabular information. But again, you might have situations where probably the table is so big that fitting that in the vision language model's image resolution is not possible. In that case, if I just go back to that particular slide, just give me 1 second. We had another way of extracting this information. So you see that we have created a specialized model which sort of extracts the table, and what we really do is that this model is then responsible for exactly extracting the table in the same format. So say for example, you have 8 columns and you have say about 1000 rows. You can extract this in a JSON format. Ask your model to extract this in the JSON format, and then that JSON format can then be used for doing any kind of query as well. Right? And then you can treat the JSON directly as another pandas data frame, and then you can ask any of your text query, and then that text query needs to then be converted to a SQL-like query or a pandas-like query, and then you can apply that pandas-like query on top of that JSON structure that you have, and then you can get the answer back. And that is also very much good. Now again, like I said, things might not always work 100%, right? That's not what we're suggesting. What we're suggesting is build this. Figure out after you do all of this, where are the places where you are still seeing errors, and try to look at the data. Because trust me, one of my biggest learning in helping organizations deploy this and build this is that looking at the data will tell you 99% of the problems. Do not just think that hey, I must model badal dunga and things will start working. That's not the right approach. Look at the data, see where the errors are occurring. You will exactly come to know what the problem is, and then you can basically find some smart way to address that. But again, very good question. Thank you.
We'll take the questions offline because time is up. But we are here outside. Catch us up. I'm sure we have a next speaker who's lined up pretty good. Let's see you. Thank you.